this portion of the video, we're going to discuss Newton's third law. This comes from section 4.5 of your textbook. In class, we talked about Newton's first two laws. Newton's third law is separate from those two. It describes how every force has what's called a Newton's third law pair, sometimes also called a reaction force. The third law can be stated as that the force that object 1 exerts on object 2 is going to be equal in magnitude but opposite in direction to the force that object 2 exerts on object 1. So that's the mathematical representation of Newton's third law of force. In words, again, this denotes the force that object 1 exerts on object 2, and this denotes the force that object 2 exerts on object 1. So what we can say for a statement is that for every force that one object exerts on another, there is a so-called Newton's third law pair So there is a Newton's third law pair force, which is also sometimes called the reaction force, that the second object exerts on the first. Now, the force, the Newton's third law pair force, is equal in magnitude opposite in direction. That's the equal and opposite part that you're probably familiar with Newton's third law. Opposite in direction, and of the same type. So what I mean by that is that if the force that object 1 exerts on object 2 is, for example, a pushing force, then the force that object 2 exerts on also 1 would also be a pushing force. If it's a friction force here, it would also be a friction force there. Force of gravity, etc. So having it be the same type can help you avoid common pitfalls that people fall into when talking about Newton's third law pairs. Another thing that I'm going to note about these two third law pairs is that F12 and F21 act on different objects. This is also a common misconception with Newton's third law. For example, F12 is a force on 2 from 1, whereas F21 is the force on 1 from 2. And so what that means when you're trying to figure out and identify Newton's third law pairs is that you can't have Newton's third law pairs that act on the same object. If I push on you, you push on me. One force is on you, one force is on me. A very common example that addresses common misconceptions is that if you have a box sitting on a table, well, it has a force of gravity acting on it. We discussed the force of gravity last class. So a question could be, what is the Newton's third law pair of the box's weight? So what is the Newton's third law pair of the box's weight? that is the box's force of gravity? Well, the answer to this is not the normal force from the table. It's a very common answer that's given. Those are equal and opposite forces in this situation, but they are not related through Newton's third law. Okay, so to spell that out more carefully, the actual free body diagram for that box will have the force of gravity downward and the normal force upward. These forces are equal and opposite, but they are not Newton's third law pairs. The reason for that is that it violates some of the key rules for Newton's third law pairs. Just because they're equal and opposite does not mean that they are caused by Newton's third law. First, they are different types. This is a force of gravity, right? So there are different types. One is a normal force and one is a force of gravity. That violates the rule. The second reason is that they actually act on the same object. They don't act on different objects. So they act on the same object. Neither of those allow it to be Newton's third law pair. Instead, you can think of it as, for the answer to this question, that if the force of gravity is acting on this box, what's the second object? What object is causing that force of gravity? And the answer to that is the Earth, right? If the Earth exerts a force of gravity on the box, that's the box's weight, then the Earth pulls on the box pulls on the Earth. So the box exerts an equal and opposite force of gravity on the Earth. So there's actually an upward force on the Earth from the box's gravity. Another example related to our box on the table is that if we look at the normal force on the box, we can wonder what the Newton's third law pair of that is. And we can decide that the Newton's third law pair of the normal force is also a normal force, which remember is just a contact force, of the box on the table. That is, the table pushes up on the box pushes down on the table. So the table pushes up on the box, so the box pushes down on the table. So you can just very methodically identify what the force is, what type it is, what object is causing it, what object is experiencing the force. And then you can use Newton's third law to identify this sort of hidden force that exists that is equal and opposite in magnitude. It is caused by the first object on the second, and it has of the same type. Right, in this second portion of this pre-lecture video, we're going to discuss the idea of friction as a force. So far we've had the normal force, gravitational forces, tension, forces of pushes and pulls, and we've analyzed problems that way, or we will. Now we're going to add back in friction, which we've been neglecting so far. So it behaves just as any of the other individual forces in Newton's second law, and we can actually quantify the force of friction, and we'll see that it relates to the normal force. Before we do that, we have to see that there are actually two types of friction. And it depends on whether the surfaces are moving relative to each other or not. There's kinetic friction and static friction. And the kinetic friction has to do with when the surfaces in contact that are causing the friction is when the surfaces are moving relative to each other. That is, that they're sliding relative to each other, sort of a skidding motion. And then static friction is going to be when the surfaces are not moving relative to each other. Now, they might be moving. For example, you put a box in the back of a pickup truck and you drive, and say the box does not slip. Then the force of friction acting between the box and the pickup truck is going to be a force of static friction. Even though they're both moving, they're not moving relative to each other. Alright, so the way that friction depends on an applied force is actually very interesting. So if we have a force of friction, the magnitude of which we're denoting as little f, which is the commonly used symbol for friction. Well, the static regime happens first, right? Let's say that you're applying a force. So here you have some magnitude of an applied force. And first, when you're not pushing at all on an object, imagine trying to push a filing cabinet across the floor. Then obviously there's no friction force. You're not applying a force, there's no friction force, or else if there was a force, the object would spontaneously move across the room, and that does not happen. So if we think about this, in the static friction regime, we would have that whatever your applied force is has to equal the force of static friction, because it's not moving relative to each other. So the sum of forces has to be 0. So the applied force then has to be equal to the static friction force. And so even if you push harder, if you will make a larger applied force, then your force of static friction has to be larger in order to match that, because it's not moving, or not moving relative to each other. So in this case, you end up with a linear relationship in this portion of the graph, where you have that the force of static friction is equal to the applied force. And again, that's because they're not moving relative to each other. Now, that's an interesting result, and it's actually one that students often forget. So you have to remember to think about it conceptually. If an object is not moving, the force of static friction actually is going to then match whatever this applied force is, because they're not moving relative to each other. So the force of static friction changes. There's a maximum value that if you push hard enough, then you so-called overcome static friction, and then the object will start moving. So that's what we'll denote here. At some point, you reach a maximum value of allowed static friction for it depends on the qualities of the two surfaces. And then what happens is if you push harder than that, so a larger applied force, then it'll start moving. So I'll finish out this graph and talk about the rest of it. The rest of it actually just looks like this straight line, so it drops down. This here is our slip point, our so-called slip point, that when you push harder than this, then you are able to get it moving. So how hard you have to push, that would be this applied force here, in order to get it to start moving. And remember, this applied force will equal that force of static friction. So how hard you have to push to get it moving. So that so-called slip point then happens at the maximum value of static friction. So it happens at F sub x max. Then what happens is now it's moving relative to each other, so you end up being in the kinetic friction regime. And the kinetic friction regime here is going to be, again, when they're moving relative to each other. And I'll write some information about it down here. So for kinetic friction, you actually have that the force of kinetic friction, F sub k, is equal to a constant, regardless of the force applied. Which is not necessarily an intuitive result, and very interesting. It has to do with the nature of friction coming from the roughness of the surfaces, sort of like every surface has some jigsaw puzzles at the bottom, and then as they move across each other, friction is actually the bumping of all these little contact points from these rough surfaces. It doesn't really matter how fast something is moving, what the force is that ends up resulting. So you have this constant kinetic friction regardless of the force applied. Now that's actually very useful for problem solving, we'll see, because the force of kinetic friction then has just one simple way of being quantified. So we have here this sort of picture where you can write the force applied, and then let's say you have some force of kinetic friction. If you increase the applied force, then the force of kinetic friction stays the same length, does not change. So the way that we quantify friction is through what's called the coefficients of friction. So the coefficient of static friction is called mu sub s. And we remember that the force of static friction is normally equal to the applied force. But what the coefficient of static friction allows us to do is it allows us to quantify the maximum force of static friction. So F sub x max is going to be equal to the coefficient of static friction, mu sub s, times the normal force. Now, why would it depend on the normal force? The normal force has to do with the weight of the object, or how hard the object is pushing down on the surface. And so again, back to this idea of this roughness of the surface, these little contact points, these jigsaw puzzles, the harder it's pushing down, the more contact there is, and then the harder it is going to get to move. Now the coefficient of static friction is something that is just determined experimentally with different surfaces, and it's going to depend on the nature of the surfaces. So what we can say then in general is F sub s is going to be less than or equal to mu sub s n. And so you have to then think about the situation and decide, is it at the maximum value of static friction? And if not, is it moving, and it will be moving relative to each other, which will then allow you to know that it's going to be equal to the applied force. Now, for the kinetic friction, because it's going to be constant, the coefficient of kinetic friction is going to be mu sub k, and we just have one standard equation. There's no inequality that is set. So F sub k is equal to mu sub k n. It's always equal to that. It's equal to a constant regardless of the motion in question. If the two surfaces are moving relative to each other, then F sub k equals mu sub k n. So what this does is when you draw a free body diagram, then you identify first whether it's static or kinetic friction that's acting. And then once you've decided, then you know that you can quantify that, and it'll be related to whatever you determined for the normal force. You just add it in as another individual force into your Newton's second law equation, where the sum of forces is equal to the mass times the acceleration, and then you use it to solve your problem. That's going to conclude our discussion of both friction and Newton's third law. If you have any questions, please let me know.